Okay, we're going to look at lesson 10-4 hyperbolas. Biologists use hyperbolas to locate and track whales based on the sounds that the whales make. So it is something that is used quite often. For a hyperbola, we're looking at what would happen if you pulled the two foci of an ellipse so far apart that they moved outside the ellipse. The result of this would be a hyperbola, which, when we were talking about an ellipse, we defined it as a fixed distance where you added these distances together to from the foci. But in the hyperbola is the difference of the distances. And so that they show that right here. A hyperbola has what's called two branches. They are symmetrical. One of the branches, or say, those are specifically symmetrical. They have two axes of symmetry. There's a transverse axis, which is similar to the major axis of ellipse. And the vertices of the hyperbola are on the end points of the transverse axis. So where the vertices on an ellipse are at the ends of the major axis, for a hyperbola, the vertices of the hyperbola are on the transverse axis. The other axis is called the conjugate axis. So with the ellipse, it's a minor axis. For a hyperbola, it's a conjugate axis. And the co-vertices are the endpoints of the conjugate axis. So the standard form of the equation for a hyperbola depends on whether it opens horizontally or it opens vertically. And here we show that. So you can see that from the graphs here, we have, if it opens horizontally, then the horizontal axis is the transverse axis. And you can see that A is on the transverse axis, so we have negative A and positive A. And the co-vertex is on the conjugate axis, so in this case the vertical axis when it's horizontal. And then you notice that the foci, or the focus, okay, those are also on the horizontal axis because it opens horizontally. When it opens vertically, the transverse axis is now the vertical axis. So A represents where the vertex is, B, the co-vertex, which is on the horizontal, and C, the focus is on the vertical also. So you've got those relationships, which are similar to an ellipse, but not exactly. Also, you notice that there's a box here around it, and the box in both cases, or the rectangle, that you'll notice that the width of the rectangle is either A or B, and the height of the rectangle is either A or B, depending on whether it's a vertex or co-vertex. But the values of A and B define where the sides are of the rectangle. And then you'll also notice that there are two lines that go through the corners of the rectangles and through the center of the hyperbola, and those are called asymptotes. Okay? Because what happened is the graph, you can see the graph runs along, right along through here, and it hits along this asymptote here, that asymptote there, and it does it on both sides. The other thing is that the relationship between the values of A, B, and C. That with an ellipse, it was C squared equals A squared minus B squared. With a hyperbola, it's A squared plus B squared. So like the Pythagorean theorem. And then here we have our equations. We have, if it opens horizontally, x squared over A squared minus y squared over B squared equals 1. If it opens vertically, you'll notice that when it opens vertically, then the y is positive and the x is negative. Otherwise, for vertices, foci, and co-vertices, they're exactly the same as with an ellipse. The only other difference is we have, down here we have asymptotes. And the asymptotes relate to those lines, and the equation of those lines, since they're centered at the origin, which means that the y-intercept would be 0, that we just have plus or minus the slope of those lines, which is the change in y over the change in x. So if it opens horizontally, b over a, opens vertically, a over b. So you can just think about it as y equals plus or minus the change in y over the change in x. So just rise over run. All right, so we're going to look at finding the equations of hyperbola. So we're going to write the equations of hyperbola in standard form. And here they give us a graph, first of all. So the first thing we need to do is identify which way this graph opens. And because we can see that it opens to the left and to the right, that means it opens horizontally. So then we're going to be using the equation that's where x squared is positive, and a squared always goes under the one that's positive, minus y squared over b squared, and just like an ellipse, it always equals 1. The next thing we need to do is identify where the center and the vertices are. The center in this case is the origin. So we can see that the asymptotes go right through the origin. And we can see that there are points here and here, which, since those are on the actual graph, those are called the vertices. And the vertices then would be, give me the points plus or minus 6, 0. The co-vertices then are on the other part of the rectangle. In this case, then, the vertical part. All right, be right in the middle of those vertical lines, which those are also at 6. So the co-vertices would be at 0 plus or minus 6. Now then, what does that tell us? That tells us that A is 6 from the vertex, and B in this case is also going to be 6 from the co-vertex. So when I write the equation then, I'm just going to put 6 in for A, 6 in for B. So we get x squared over 6 squared, which is 36, minus y squared over 36 equals 1. And that would be the equation of our hyperbola. Now the one thing is that this is a little bit tougher than an ellipse just because there's a little bit more information there that we use. So let's look at another example. Here we have a hyperbola with a center at the origin, and the vertex is at 4, 0, and the focus is at 10, 0. So I'm going to go ahead and plot those points first. 4, 0, 10, 0. Now, a reminder that if we have a vertex at 4, 0, we also have one at negative 4, 0. If we have a focus at 10, 0, we also have one at negative 10, 0. Well, when I determine which way this opens then, since the graph is always connecting the vertex, that means then that this graph is going to look something like this. I don't know exactly what it is. I'm just going to give it an estimate here, draw it, okay? Which means then it would open horizontally. So once again, I'm going to have x squared over a squared minus y squared over b squared equals 1. And just like in the ellipse, the vertex and the focus tell us something specific. The vertex helps us find the value of A, and the focus helps us find the value of C. So we need to find, for our equation then, we need to find what A and B equal. In this case, they give us A and C. So we have to use that relationship that looks like the Pythagorean theorem. So let's move this down a little bit here. There we go. So the relationship between A, B, and C is that A squared plus B squared equals C squared. So in this case, A is 4 and C is 10. The distance from the center, which is the origin, to the vertex, distance from the center to the focus. So we put 4 in here for A and 10 for B, or for C. So we would have 100 minus 16, which would be 84. So B equals the square root of 84, but I really only need to know the 84 because it's b squared that I'm going to use anyways. So here we're going to get x squared over 4 squared, which is 16, minus y squared over b squared, which is 84, equals 1. And notice one of the things that can be true about a hyperbola that's not true about an ellipse is that the value of a can be less than the value of b. So in this case, the value of a is much smaller than the value of b, considering it's 4 compared to approximately 9. And so there we have the equation of the hyperbola that has a vertex at 4, 0, co-vertex at 10, 0. And if we want, or focus, and if we wanted to actually graph the co-vertex here, they would be a little bit more than 9. So they would be here and here. So we could actually, from that information, I could draw a graph of that and put it up here. But we're going to do that with the next problem. Okay, as we continue on, we're going to look at hyperbolas then that are centered at a different point than the origin, the point HK. And this is the same HK like we were using with an ellipse. And so if you look at the equations here, they look almost exactly the same as the equations of the ellipse. The only difference is that we have a minus. So we are actually going to be subtracting, oops, there we go. And so in both these cases, it's a minus sign, where in ellipse, it's a plus sign. Everything else is basically the same as it is for an ellipse. The only difference is down here where we have the equation for the asymptotes. Now when we put HK in there, we have the values in our asymptotes also. And if you remember, all this is just the point slope form of the equation of a line, which if you remember what that said, it was y minus y1 equals m times x minus x of 1. So this equation for the asymptotes is nothing different than what we've used before. We actually used it a couple lessons ago when we were doing tangent lines. And when you write your answer for the asymptote, go ahead and put it in this form right here. And all I did is move the k from the left side of the equal sign to the right side of the equal sign. And so you have y equals. But don't simplify that because it gets a little complicated with a plus or minus, and that's not necessary. All right, so we're going to go ahead and find some specifics. Find the vertices, co-vertices, and asymptotes of each hyperbola. Then we're going to graph it. So we need, for graphing, we need to know a couple things, all right, before we get to the vertices. We need to know where the center is. Okay. In this case, since there's no h or k, it would be 0, 0. And we need to know which way it opens. Does this open horizontally or does it open vertically? And since x is positive, that tells me that it opens horizontally. So when we find the vertices then, we need to find the value of a in this case. And so a would be 7 square root of 49, and b would be 3. Now, to find those vertices and co-vertices to write them down, I could use the expressions up here, but what I'm actually going to do is I'm going to graph them first, and then we'll talk about where exactly they are and how I know they're there. So I'm going to go from the center. Since it opens horizontally, I'm going to go 7 to the left to negative 7, 7 to the right, positive 7. And then b is under the y, so I'm going to go up 3 and down 3. And so all I really did here is that I took 0, 0, and I added 7 to the x coordinate and subtracted 7 from the x coordinate, which gave me plus or minus 7, 0 for the vertices. For the co-vertices then, because b is under the y, y is negative, I'm just going to add 3 and subtract 3 from 0, which gave me 0 plus or minus 3. Then the asymptotes are going to be y equals, since h and k are both 0, I don't need them, y equals, and it's the change in y over the change in x. In this case, the change in y is b. The change in x is 7. So we'll have plus or minus 3 over 7x. And there's my asymptotes. Okay? And now we need to graph it. So after I've plotted my points here, and I can put the center in there too. After I plot those points, I'm going to draw a rectangle. And my rectangle then is going to be a dotted line, and it's going to go from y value to y value as height, and x value to x value as for the length. And so that'll look like this. Right. So now when I graph the asymptotes, I'm going to graph them too. The asymptotes then are going to go through the corners of the rectangle. So I'll start at one corner, go through the other one. All right, and for mine, I have to do it this way and then back. And the same with the other one. And your asymptotes should go right through the center of the graph, which mine does. Okay? So I have my rectangle, I have my asymptotes. Now to draw the graph, opens horizontally. So then I'm just going to go through here, hit the point, and come back. And remember what asymptote is? It means the graph gets closer and closer to it. Doesn't actually touch it. It gets closer and closer. And there's that graph. All right. Now, we're going to look at another example. And this one is a little different because the center is different. So once again, we're going to figure out which way is it open and where's the center at. So in this case, the center is going to be at the point 3, -5. And once again, because x is positive, it opens horizontally. So, vertices then. Well, first of all, the value of a. A in this case is going to be 3, square root of 9, because that's under the x, which is positive. Value of b is 7, okay, under the y. So I'm going to go ahead and graph those points. So I start with the center. The center is at 3, -5. All right, and then I'm going to go, a is 3, it opens horizontally, so I'm going to go 3 to the left and 3 to the right. And b is vertical change, so I'm going to go up 7 and down 7. Oops. Now, here's the thing, how we understand those points. That the change in x means I'm going to take the 3 from my center, and I'm going to add 3 to it, which will give me 6. Subtract 3 from it, give me 0. And that's where those equations, all these things up here, okay, that's what they all relate to. All these things are talking about finding those points, and that's all we're doing. But I'm doing it all from the graph. So we've got the point 0, -5, and you notice, because we changed the x value, the y value stays the same. And then to get the covertices is a change in the y value, so that means my x value stays the same. And I'm going to take -5, my y value, and add 7 to it. That'll put me at 2. Take 7 from it, that'll put me at -12. So my asymptotes then are going to be y equals plus or minus, and I'm going to write this out again, change in y over change in x, x minus h plus k. All right, now that's that general form we looked at up by all those equations. So then, what's my change in y? Change in y in this case is b, which is 7. Change of x is 3. H is 3, so I'll put that 3 in for h, and k is -5. And so I have the equations for my asymptotes. So now I'm going to put my box around this. So here's my height, my width. Continue to draw that box. And And then, like I said, that your asymptotes then are going to go right through the corners, and which should go right through the center then. And then once again, this one opens horizontally too. So this one's going to be really wide, and that happens sometimes. So you hit the point, and then try to stay close to the asymptote. And there's a graph of your hyperbola. And that's the thing is that you notice the difference between this one and the previous example, the fact that in this case, B is larger than A, and so it's going to be a lot bigger, and that can happen with a hyperbola, but cannot happen with a ellipse.